Alright, so let us recall what we did in the last class. We talked about matrix multiplication. So, the idea of matrix multiplication was to look at things from a different perspective. So, what we had learnt in our school was a matrix multiplication which was based on entry wise. So, the idea was that given a matrix A, m cross n, B is say n cross P, so that we can multiply here this n and this them are same equal here, and therefore, we could define A B and write it as a matrix of the size m cross P, fine. Then we had this entry of this matrix as A I j, entry of this matrix as B I j, and once we have that, we wrote this as the entry of this matrix as C I j, and then C I j was nothing but summation over k is equal to 1 to n. This n was the one that was here, all right, A I k B k j. So, we have to remember this formula also, this is very, very important, but at the same time there are other multiplications also which we wanted to understand. So, let us look at other things once more. So, this was one matrix product that we learnt in our school, what is called entry wise. So, we are looking at each entry of A B here. So, we are looking at each entry of A B. Now, we would like to understand the other one, which was row method of multiplication, row method of matrix multiplication. So, recall what the idea was. The idea was that you have the matrix A, which is, so look at the rows of the matrix. The first row is, this is the first row of the matrix, this is the second row of the matrix, and you have the mth row of the matrix. There are m rows of this matrix, fine. Each of these rows have size 1 cross n, B is of size n cross P, and this will imply that I can talk of A of the first row times B, and this is a 1 cross P matrix, fine. And therefore, when I want to talk of A B, I could write it as A of first row times B, A of second row times B, and so on, the mth row times B. This was one way of writing it. The second method was looking at the column method. Of matrix multiplication. So, there the idea was that we leave A as it is and write B as the first column of B, second column of B till the pth column of B. You can write like this. If I look at this B, this is of size n cross 1, each of them is n cross 1, and therefore, we can talk of A times the first column of B, and this is nothing but A is m cross n, this is n cross 1. So, this is a matrix of size m cross 1. So, I could write A B as A times the first column of B, A times the second column of B, and so on till A times the last column or the pth column of B. So, A B was equal to this, A B was equal to this, and this was the entry wise. So, what we have done is there is an entry wise product, then computing the matrix product using the rows. So, you are looking at how do I get the first row of A B, the second row of A B, and the mth row of A B, and this was getting the first column of A B, second column of A B, and the last column of A B. Then there was another product that we learned. What was the matrix product in the general setup, where what we had was, we wrote A as, so here I write A as again first row, second row and the last row. So, you have to be careful. What is the size of this matrix? The size of this matrix is 1 cross M. We can look at B as first column, second column and the pth column. So, this is of size m cross 1, m cross 1, sorry, n cross 1, not m. So, this was n here, all right. So, this was n, 1 cross n, n cross 1, n cross 1 till n cross p, and this was 1 cross n. So, if I see this, I can multiply this with this with this, and so on. So, the matrix product that we write here is A of this into B of this, A of this into B of this, and so on. In general, if I look at this entry, which is the I j entry, then this corresponds to ith row times the jth column of B, and this is what our entry C I j was. This was one way of writing it. So, here we broke A in terms of the rows, all right, we wrote it in terms of the rows, and B in terms of the columns, and we could get C I j, the first matrix product that we learnt in our school. Now, the last one that I wanted you to understand was, write A in terms of the separate ones. So, write A in terms of the columns. So, A is the first column is, this is the first column, the second column, and this is the last column of A. Write B in terms of the rows. So, B is, this is the first row of B, the second row of B, and the nth row of B. Each of them is nothing but 1 cross P, all right, and here each of them is m cross 1. So, I can multiply A B. So, if I multiply A B, what I get is this times this. So, it is nothing but the first one times the first one of B plus the second column of A with the second row of B, and so on till the last one, which we wrote it as summation over k equal to 1 to n, the kth column of A times the kth row of B. So, this is a matrix product. If you look at each of them is of size m cross 1 times 1 cross P, and therefore, what I get is m cross P. So, each of them is a matrix of the proper size of the size of A B. So, the size of A B and the size of this, you can see that they are same. So, these are the matrix product that we learnt, all right. Now, let us look at some of the properties. I would like you to keep track of all of them, fine. So, remark. So, first thing is that if A is m cross n and B is some p cross q, then A B is defined, find if n is same as p. 2, B A is defined if, so B is size p cross q, this is the size of B, the size of A is m cross n. So, what we need that this should be the same. So, we need that q should be equal to m, fine. So, we have examples here where we have seen that. So, what we are saying is that it may happen that AB is defined, but BA may not be defined. BA is defined, AB is not defined. Even if both A and B are defined, so if I take A as M cross N, B as N cross M, then AB is defined and the size of AB is M cross M. BA is also defined and the size of BA is N cross N. So, even if they are defined, they have different sizes. So, let us take an example. So, I define A as say 1, 2, 3 and B as minus 1, 2, 3. Then if I look at AB, the size of AB is 1, 2, 3 times minus 1, 2, 3, which is nothing but minus 1, 2, 3, minus 2, 4, 6, minus 3, 6, 9. So, it is a 3 cross 3 matrix. But if I look at BA, BA is minus 1, 2, 3 times 1, 2, 3, and this is nothing but minus 1 plus 4 plus 9, which is minus 1 plus 13, which is 12. So, here it is a 1 cross 1 matrix and there it was a 3 cross 3 matrix. So, the sizes could be different, fine. It may happen that AB and BA both are square matrices. So, if AB and BA are both square matrices, then AB is defined and BA is also defined, both are of the size M cross M, but still it can happen that they are different. So, AB and BA need not be the same. So, for example, let us look at an example here. So, example I will take A as 1, 1, 1, 1 and B as 1 minus 1, 1 minus 1. Then this will imply that if I look at AB, so let us look at the matrix product. So, I am looking at I want to get the first row of AB. The first row of AB will be 1 times the first row of B times 1 times the second row of B, and therefore, it will give me 0, 0. Similarly, here also it will give me 0, 0. But whereas, if I look at BA, BA is now this times this. So, it will give me 2, 2, minus 2, minus 2. So, the sizes are same, everything is same, but the matrix product AB and BA, they are not the same. One is the 0 matrix, the other has some rank that will come to afterwards. We have some non-zero entries, but at the same time we will see at a later stage that when we come to eigenvalues, eigenvectors, that they have similar structure. Same thing happens in the case of 3, where the sizes of AB and BA were different, but still we will see that lot of things are nice. The next thing we would like to look at, so some more examples we will look at matrix product, that will come to afterwards. So, some now definitions now, definition. 2 square matrices are said to commute if A times B is same as B times A, fine. We need this basically to look at algebra from our point of view. So, in general what happens is, we have already seen that in general AB is not equal to BA, and this will imply that I cannot talk of A plus B square. So, this will not be equal to A square plus 2AB plus B square, even though this is equal to A square plus AB plus BA plus B square. So, this part is fine, but this is not allowed. So, what we had learnt in school algebra was A plus B whole square is A square plus 2AB plus B square. That is not true in general now, alright. So, you have to be careful when you do matrix product. And not only that, we also saw in the previous slide that I have got here A and B, they were non-zero matrices, but still the product A B could become 0, all right. So, let me write that also as a point which is important, that we can have non-zero matrices. So, each entry there is non-zero. We can have non-zero matrices, but their product can be a 0 matrix. We had looked at a similar example earlier also when I was trying to look at matrix product. So, there for example, so let me take an recall that example also, which is a very important example when you come to eigenvalues, eigenvectors. So, I have a matrix A which is upper triangular, I can take it as lower triangular also. Suppose its entries are A11, A12, A13, 0, A22, A23, 0, 0, A33. So, it is upper triangular matrix. I want to look at the product A minus A11 times identity times A minus A22 times identity and A times A minus A33 times I want to multiply these 3 matrices and see the product, what this product is. So, if you look at the first entry here, this part, this matrix is 0 here, A12, A13, 0, it will be A22 minus A11, A23, 0, 0, A33 minus A11. This matrix is nothing but A11 minus A22, then you have A12, A13, 0, 0, A23, 0, 0, A33 minus A22, and I have this part that I am leaving as it is. So, if I look at this matrix product again, what we see is, recall that the first column here is 0. So, what happens in the first row is immaterial to us, because I am going to multiply. So, if I look at this column times this, it is this entry is getting multiplied to the first column. So, that is 0, this entry is 0. So, this part will give me 0, this is 0, with this multiplication will give me 0. So, the first column of this matrix will be 0. Again here, if I look at the second column of this product, it will be A12 times 0, which is 0, 0 times A12, that is the second column, and again 0 times the third column here, which will again be 0. And here I will have some entries, I do not know what they are, they will have some entries, fine. So, this is the product of the first 2 blocks, first 2 matrices. Now, let us multiply with the third one. The third one is A minus A33. So, it will be A11 minus A33, A12, A13, 0, A22 minus A33, A23, 0, 0, 0. So, now what you see is that the 2 columns are 0, and therefore, the first 2 rows of this part is not going to play any role as such, and therefore, this whole product will be the 0 matrix, fine. So, this is what you have to understand, that if you can see somewhere that there are zeros coming, you can play with these zeros with the understanding of row product and the column product, fine. Let us go to the next part, some theorems related to these, and then I will again come back to some examples to make you have a better understanding of things. So, theorem. So, I have got matrix A, which is M cross N, B is N cross P, C is P cross R. They are, all of the entries are coming from real numbers itself. You can take complex numbers, rational, whatever it is, fine. Then we have these results. 1, associativity holds. So, A times B C is same as A B times C. So, what we are saying is associativity hold. So, we are saying that matrix product is associative. 2, we also have a scalar multiplication. So, how does the scalar multiplication behave? So, K times AB is same as Ka times B is also equal to A times KB, where K is a scalar. Then it also behaves nicely with addition. So, A times B plus C, that is distributive laws hold, is same as AB plus AC. So, the important thing here is, in this case, if you look at this case, B and C are not meaningful unless C is of the same size as B. So, here we will assume that B and C have the same size, otherwise the matrix product was not meaningful. In the previous ones it was meaningful, fine. So, accordingly, so what will happen is that there will be times when I will not say the size of the matrix, all right, but when I write the matrix product, you will have to assume that the sizes make sense, so that matrix product makes sense, all right. And also you have to be careful in the sense that if you can find out that the sizes of the matrix match to define a matrix product, then you will surely get some nice result or the other, all right. So, just be careful about matrix product. Wherever you can get the size are similar, you can define matrix product, you are bound to get something nice, all right. The fourth thing that would like you to understand is, now I want to take A as a square matrix n cross n. Then for every A, whatever A you take, you have identity matrix, so that A times I is same as I times A is A. So, recall what was I was a matrix in which the entries were, so 1 0 0 so on, 0 1 0 so on, 0 0 1, and this one built up here, and we had here 0 0 0 and so on, fine. So, I3, so I2 was 1 0 0 1 and so on, fine. So, keep track of that, you will need it. Now, so we have been able to relate the matrix product with respect to a scalar multiplication, with respect to addition. We had also learnt transpose and conjugate transpose. So, let us relate this also. So, what we would like to say is that if I want to talk of AB transpose, fine, then it will turn out to be B transpose A transpose. Similarly, conjugate transpose of AB will be equal to B star A star, all right. So, look at here, A is of size m cross n, B was of size n cross p, together the product was m cross p, fine. Look at B transpose, all right. So, this was the size of AB, size of AB was this. So, therefore, the size of AB transpose is P cross M, fine. Let us look at the size of B transpose. Size of B transpose is P cross N, size of A transpose is N cross M. So, this N and N cancels out, you do get M cross P cross M. So, you can see that the size of the two sides are equal. Similarly, here also the sizes make sense. So, we just have to check whether the entries are same or not. So, let us prove that part. So, let us look at, suppose I have the matrix AB transpose, I want to look at the ij entry of this. So, by definition ij entry of this will be equal to ji entry of AB. That was the way it was defined. The transpose was rows becomes columns, columns becomes rows. So, this is what it was. I can write it as summation over k equal to 1 to n or some size whatever it is, all right, A of j k into B of k I. So, this is important. So, this k and k cancels out, remember it please, cancel out, fine. But what is A j k and B k I? So, I can write this as summation k equal to 1 to n. A j k is nothing but if I look at A transpose, it is the Kj entry, and what is Bki? Look at B transpose, it is the Ik entry of that. All right. I can write this back as k equal to 1 to n B transpose Ik into A transpose Kj. So, now here k and k matches, and therefore, I can talk of this as B transpose A transpose Ij. So, you can see that they are equal as such. All right. So, I would like you to try the same thing for the star also, prove it yourself. All right. So, once you have done that, you can also recall that what we had was that A transpose transpose was A and A star was A. So, it will hold for matrix multiplication also. For multiplication as well. All right. Now, some examples. So, one of the examples that I wanted to do, all right. So, I will just write that, and maybe we will discuss it in the next class for a better understanding how to use it. So, or I will just end it here itself, I think, and look at the examples in the next class. All right. Thank you.